So our next speaker is Christos Kastrisios from the University of New Hampshire.
So hello everyone, can you hear me? Yeah, try again. Thanks. My name is Christos Kastrisios. As said, I work for the Center for Coastal and Ocean Mapping. I'm research assistant professor there. And I'm going to talk about our work with Colin, Ware on the visualization of data quality sectors on electronic navigational charts. A few background information. Ocean shipping industry is the main mode of global trade, and around 90% of goods are carried over by ships, as it is economically and environmentally efficient. However, maritime accidents can cause harm to the environment and local economies, and of course result in loss of life. A major fundamental tool for mariners used to safely navigate their vessels is the nautical chart, which contains information about depths, dangerous navigation, aids to navigation, and other relevant marine and coastal environment information. The nautical chart is, the bathymetry of nautical charts is a jigsaw puzzle of surveys, data collected at different times using different techniques. Here's an example of the surveys used for charting the areas from Boston to New York. So data collected with modern high-resolution techniques such as multi-beam echo sounders with full seabed coverage may coexist with data collected as far back as the 18th century with methods such as handheld lead lines. And of course, the same with the positioning methods where you can see differential GPS and even sextants. So the data quality on paper and electronic navigational charts is portrayed using overlays of polygonal sectors, each one assigned a category zone of confidence, as we call it CATZOC, based on the positional and attribute accuracy of measurements, as well as the data completeness. We have 6 categories, A1, A2, B, C, D, and U for unassessed data. And currently, ZOC is portrayed on electronic chart displaying information systems as a series of stars, as you can see here, where the concept is that more stars represent better quality data. Reports have shown that maritime accidents could have been prevented if data quality had been better accounted for, and this table exemplifies the importance of better communicating data uncertainty to the end users. You can see that more than 50% of coastal ENCs, this is data from 32 nations globally, more than 50% of the coastal ENCs are compiled with poor quality data, and only a small portion is with good, high quality data. Of course, beyond coastal waters, the situation is even worse. So the question is, can we do better? We believe we can, but before we get there, let's see. I didn't discuss the problems of the current symbology. As you can see, a summary is the clutter that the symbology adds. So you can see where the pointing arrows are. When it overlaps, when the stars overlap the depths, it's clearly impossible for the end user to read the depths. Then, contrary to cartographic principles, it adds more visual weight in areas of high quality data, low uncertainty, whereas in low quality data, the view is relatively clearer. It's not intuitive. You need to count stars in order to understand what is the CATZOC level. This is me, I would say, after 25 years in the field, still counting. And may not fit in small areas. It's the question marks, example of the question marks over there. And all these, because of all the above, continuous zoom in and out is required by the end user to resolve any conflicts. And lastly, as you can see, it dominates the screen, particularly in dusk and night modes. So we started with setting the requirements that the new symbology must satisfy to be effective for the application, and that includes things such as minimally interfere with other chart information and be easy to memorize. Before I move on, I need to explain that the nautical cartography is underway major changes, where one of the things is the transition from the category of zone of confidence to the quality of bathymetric data, and this has to do with how it is incorporated in the electronic systems. But in terms of the criteria for the different categories, nothing has changed. We have one more category for oceanic, where depth is not of our concern. And also we have the transition from these alphanumeric codes to a numerical scheme 1 through 5. So we started with reviewing the visual variables for the performance for the requirements, and we concluded, we thought that the best solution would be the countable textures, as we call them, a sequence of textures consisting of countable elements, see-through textures. And the advantages of see-through textures is that they are minimally used in current TechDis displays, whereas if they consist of open meshes, they can minimally interfere with other chart information. And of course, the combination can be intuitive and it also achieves good visual hierarchy. We proposed two coding schemes, one consisting of lines and one of dot clusters, where the main principle is that the lines or the dots in the clusters correspond to the quality of bathymetric data. You can see one line for quality 1 or one cluster, two crossing lines for quality 2, or two dots, three crossing lines, one single and one double line, and so on and so forth. For comparison, we developed three more coding schemes, two based on ideas previously expressed within the hydrographic community, one consisting of opaque colors, and one with different levels, with variations in color transparency and saturation. To overcome the problems of color fields, such as obscuring the underlying bathymetry or color blending, we also developed the color textures coding scheme. This is how the 5 coding scheme look over a section of a chart. We have the lines, lines, opaque colors, the dot clusters, transparent color, and the color textures. Before I move to the survey and the results, I would like to demonstrate how we believe things are improved with the new coding schemes. Here's an example of the stars and the lines for quality 1 data. You can see that depths are not visible here, whereas with lines, the depths are clearly readable. Here on the top side, we have quality 1 and quality 4 with stars and with lines. You can see that, as I said, more visual weight is added in the low uncertainty data, the good quality data, whereas in our case, we add more visual weight in the poor quality data, the low quality data, to act as a warning, but still depths are readable. And about what I explained, that it's not intuitive, you need to count stars, whereas directly one line is quality 1, 4 lines is quality 4. And the problem that stars may not fit in small areas, here's an example. We don't really know if this is 5 or 6 stars, or this is 2 or 3 stars, whereas again with lines, quality 1 and quality 4. And lastly, the problem with stars dominating the screen. This is how it looks in day bright, and in dusk mode, the situation is certainly improved, and now bathymetry stands out as the top layer. Now, to test the performance of the 5 coding schemes, we developed a user survey. We ran an online survey with the support of 3 maritime centers that we have collaborations. And the survey was intended for professional mariners and others using charts in their profession, such as cartographers and hydrographers. So we had the consent section, the introduction section where we explained the problem, and also in the end we had the demographic section where we collected the information about participants. And in the evaluation section, we had 4 areas. In area 1, all 6 quality categories are displayed, same in area 1 dusk, which was meant to evaluate the quality in the 5 coding schemes in dusk ECDIS mode, whereas in area 2 we only had 2 different quality categories displayed, and in area 3 only 1 category was discussed. So participants were asked to rate the performance of the coding schemes using a Likert 0 through 6 scale, where 0 was for exceptionally bad performance of the coding scheme, and 6 was for a great performance of the coding scheme against the question that we asked. And also we had one objective question where we asked participants to identify what was the ZOG, the quality of bathymetric data in area 3. After the 16 in total subjective questions and the one objective question, we asked participants to rank the 5 coding schemes from best to worst, or worst to best. 5 was for best and 1 for worst in day, bright, and dusk modes. To supplement the Mariner survey, we also carried out an objective in-lab experiment where we used an in-house developed software to create chart-like displays as the map background for each trial, with the aim to eliminate any familiarity effects and easily tuned stimuli for each trial. So the task for the participants was to enter the number of the quality of bathymetric data where the marker appeared. Where the marker appeared. And 2 experiments were carried out, one with the key present and one without the key present shown. And time to respond and errors were the dependent variables. Now, to summarize the results, the 2 proposed coding schemes of lines and textures, lines in blue and dot clusters, lines in blue and dot clusters in gray, were performed the best and second best in user rankings in both day, bright, and dusk modes. Together, they received more than 70 and 60% of user best ranking, meaning 5. Among the 5 coding schemes, lines received the most positive ratings overall, besides being participants' first choice in user rankings. It also received the highest mean rating throughout the survey, and it was the only coding scheme with mean ratings over 3 in all 4 evaluation areas, and against the 5 requirements that we set for the application. It was followed by dot clusters and opaque colors, whereas transparent color and color textures performed generally worse, and particularly the latter, contrary to what we expected. Frankly, we believed it would do better than that. Now, in terms of the objective online survey question, the lines and dot clusters resulted in the least error rates and also received the best evaluation in the subjective questions that followed. We are not presenting this here. Whereas, as you can see, the transparent color performed the worst. And in terms of the in-lab control experiment, the same for dot clusters produced the fastest response times and lowest error rates, followed by lines and opaque colors. And again, transparent colors performed generally the worst in both. Now, the statistically significant differences in these graphs are denoted by the letters. So if the bars share a common letter like this situation here, A and AB, that means it's not statistically significant, whereas if they don't share a letter, they are statistically significant. Now, as we saw, textures were the most preferred coding scheme among users, among participants. As we said, they received more than 70 and 60% of the best rankings and also received the best ratings throughout the survey. However, a large portion of participants as well ranked the color schemes with, like 30 and 40% of participants rated color schemes as the best, as their best choice. So this, along with the hierarchical clustering analysis that revealed a cluster of the dot clusters and lines and the broader cluster of the color schemes, that suggests that 2 groups of users existed for this particular survey, of course. One with preference to textures and one with preference to colors. So to accommodate both groups and preferences, we recommend to the IHO, the International Hydrographic Organization, relevant bodies, that two coding schemes are made available to new ENCs, one consisting of textures and one of colors. Now, to put the results of the survey into the greater context, if we can, there are certainly differences. Results are consistent with previous studies that recommend textures for signifying uncertainty for aerial objects with coincident visualizations for the ordinal level. Opaque colors perform well in emphasizing worse quality areas, which probably contradicts previous studies, but maybe the fact that in our case it performed well, it's possibly because of the use of cold to warm colors. Further studies are required for this one. For the transparent colors, which is a mixture, as I said, of transparency and saturation, transparency is often cited as a good metaphor of uncertainty, contrary to saturation. But as I said, again, this also performed well. But the main problem of the color schemes was that, as we saw, when all quality areas were displayed, all the different areas, they performed well in signifying worse quality data. But when we saw them fewer levels, that's when the color schemes performed worse. And this is possibly something that we need to consider. If, for instance, the mapping product is to be zoomed in and out and fewer levels are to be shown. In the future, we would like to investigate how the countable textures could be extended for other applications as well, possibly with, for instance, converting the surface to steps, like with series of 0.5 or 1, 1.5, 2, and 2.5 of standard deviations to provide 5 steps, or extend to more steps, but maybe in this case we could miss the at-a-glance recognition of the category. And this concludes my presentation. If you have any questions, thank you.
We do have time for a few questions. We have somebody online. Can you open online? So whoever's online, go ahead and ask.
Hi, can you hear me?
Yes, we can.
Great. Well, thank you for sharing this very interesting work. And I do a lot of uncertainty visualization myself, but not in nautical charts. So I'm not an expert, but I'm also curious to hear your thoughts, because I'm not sure how homogeneously or uniformly the uncertainty in your data is distributed, because I think the symbology can be very difficult to follow if you have a very heterogeneously or non-uniformly spread uncertainty. I'm curious to hear if you made any observations in such regions, if you have any in the nautical charts.
So if I understood correctly the question, you are asking if it was a continuous surface, for instance, of uncertainty, right? Rather than distinct.
Exactly. Maybe you have not clusters of uncertain regions, but really abrupt changes. You know, sometimes in if a raster image, you have one pixel has a very different uncertainty than the other, and things like that.
Yeah, I understand what you're saying. So that's why I said in the end that we would like to investigate how we can extend this countable textures concept to other applications, because in nautical charting, as maybe you can see here, this is actually how it is encoded uncertainty. I mean, there are other ways to encode uncertainty in nautical charts, but for this particular thing that we're discussing, we have sectors of aggregated quality levels. So based on the depth accuracy, the position accuracy, and the completeness of data, if it is full seabed coverage, and if feature detection has been achieved, then we assign one of these category zone of confidence categories, as you can see, either A1, A2, B, C, D. So we don't have a continuous change between the two. You would see a polygon that may be assigned the A1 or quality 1 in the new ENCs, and the very next polygon, because it comes from a different survey out of this jigsaw puzzle, as I explained, you have a different category. You can have a quality 3 or quality 4. So we don't run into the problem where we have this transition, the continuous transition from one pixel to another. But truth is, based on the Another thing is that based on the scale of the product, eventually some of these small survey areas can become 1 pixel, if you know what I mean, very small. And there we follow cartographic rules, whether we enlarge these areas or we collapse, we totally remove these areas depending on whether they are good or bad quality data. Does this answer your question?
Yeah. Yes. Thank you. Thank you.
Thanks. But truth is, again, if I may say that what you're describing, it's something that applies to nautical charting when you navigate in confined waters like navigable channels or we are approaching ports. So this is another application, the precision navigation application as it is known. So, and this is a different project. We are also investigating this, how other ways to display, to encode uncertainty and visualize uncertainty on charts.
Thank you.
Thank you.
Okay, we are running a bit over time, so thank you very much for the presentation.